All right, so we're reacting carbon monoxide with steam, and we're producing carbon dioxide gas and hydrogen gas. The equilibrium constant for this reaction is given to us, and it's 5.10. That's our Kc. They would like for us to calculate the equilibrium concentrations of all species. So everything in the system, they want to know what their equilibrium concentrations are if 1 mole of each component is mixed into a 1 liter flask. And so those represent our initial values of everything. And so I recognize this as an ICE problem or an ICEE chart problem because I'm given initial values and they want me to solve for equilibrium values. Anytime I see those two things in the same problem, that's key, a red flag almost to let us know that, hey, we're going to make an ICE chart. So an ICE chart always starts with a balanced chemical equation. All right, so I have my balanced chemical equation. All coefficients are 1, 1 to 1 to 1 to 1 mole ratios. Next thing, set up your ICE chart. All right, I have my skeleton of my ICE chart. Remember, I is for initial, C stands for change, or you can think of that as the coefficient part. E for equilibrium in terms of X, and then you have E for equilibrium, and those are going to be reported in molarities or your concentrations. And remember that these two E rows, they are equal to one another. And that's how a lot of times we're going to end up solving for X. And so now we're going to plug in what we know about this system. Our initial values, we're putting in 1 mole of everything initially into a 1 liter flask. So our molarity, 1 mole over 1 liter, everything initially is 1 molar. Nice, easy math. Next step, let's do the change. Well, I don't know which direction this is going to proceed based off of those initial values right now, just by looking at them. Because I don't have anything that's initially 0, it makes it a little bit harder to determine which way the reaction is going to proceed. So what you have to do, anytime that you don't have a 0 in the initial row, you're going to have to calculate Q, then compare Q to K to determine in which direction the system is going to proceed to establish equilibrium. Is it going to move in the forward direction, or is it going to go in the reverse direction? And so off to the side, we're going to have to calculate QC. So I have my QC expression. I go and look at my initial values from my ICE chart. Everything is a 1 molar. And so we're going to plug in 1 molar into our QC. Remember, QC is something that we calculate for non-equilibrium conditions. And so that's exactly what our initial conditions are. We don't know if it's at equilibrium or not. We're kind of testing that. So we're going to plug in our initial values. So everything initially has a molarity of 1, makes our calculation of QC very easy. QC is 1. Now you got to do the next step. After you calculate Q, you always got to compare Q to K. So writing it in alpha order, K and then Q. I know Q is 1 that we just calculated above. Now I'm going to go back to the question and look for the value of K. K is 5.10. So we can see here that K is greater than Q. And so now I got to think. To reach equilibrium, Q has to equal K. Well, this is not at equilibrium because they are not equal to one another. So Q must increase in order for the system to establish equilibrium. And since Q is products over reactants, we gotta make more products. And so that means we're going to proceed in the forward direction or to the right. And this means we're going to move to the right in our ICE chart. We're going to add to the product side for that change row. So we are proceeding in the forward direction. Okay, so I am going to draw this red arrow here so that we know for this change row, I had to calculate Q, compare Q to K to decide which direction the reaction is going to proceed. And we just said it's going to proceed in the forward direction. So that means we're going to use reactants and make products. And the change row is when we're going to use X and the coefficients from the balance equation. Next, for the equilibrium row, in terms of X, you're combining the initial and the change rows. Leave it in terms of X. Okay, so looking here at our information, I can't plug anything into this last row in my ICEE chart. I wasn't given the equilibrium concentration of any chemical species in our system. So I can't set these two equilibrium rows equal to one another right now because I don't have any values in this bottom row to set any one of these things equal to it. So there must be another way for us to calculate X. And that's through the equilibrium constant expression. So I'm going to write out my Kc expression. I'm going to plug in the numerical value for Kc, 5.10. And then I'm going to plug in the equilibrium concentrations of the chemical species in terms of X. So I'm grabbing the values from my ICE chart. I'm going to grab this row right here. And I'm going to sub in those molarities for each one of these chemical species. Okay, I substituted them in, and if it helps you out, you can drop that molarity sign I've done here. I can drop that coefficient of 1 because I understand it to be a 1, just to make it a little bit easier for the math. Now we're going to solve for X. You'll notice here in the numerator, you have the quantity of 1 plus X times the quantity of 1 plus X. That can be rewritten as quantity of 1 plus X squared. In the denominator, we can do the same thing. I have the quantity of 1 minus X squared. So we have a perfect square in the numerator and a perfect square in the denominator. And so this allows me to take the square root of the right side. And that means I have to take the square root of the left side. Okay. So I get 2.2583 on the left, and I'm going to continue using that value in my calculator, but on my paper, I'm just going to keep 4 decimal places. And then on the right-hand side, this is the nice part about having that perfect square. You just end up with 1 plus X over 1 minus X. And now we're going to solve for X. I'm going to cross multiply here, rearrange, and solve for X. I get an answer of X is equal to 0.386 molar. Now that I know the value of X, I'm now going to sub this value of X back into my ICE chart. So I'm going to insert it back into your ICEE chart. So for our carbon monoxide, it is 1 molar minus 1x, or in other words, minus 0.386 6, and that's in molar. And solve that, and I'm going to set up the rest, and I'm going to go back and calculate everything. Okay, all of my X values are substituted in to my ICEE chart for that very last row. That's where I sub in the X. And then my last step here, guys, I'm just going to finish up the calculations. And there you have it. I have my molarity values for all the chemical species when they are at equilibrium. So you can see here are my final answers that I'm putting this blue box around. How my ICEE chart is a very good way for me to keep all the information organized. I start by writing my balanced chemical equation. I write my initial values. I determine the direction that the reaction will proceed to establish equilibrium. In this case, I had to calculate Q. We're moving in the forward direction, so that means we're going to add to the product side, make product. My next line is equilibrium in terms of X. And then to solve for X, for this problem, since they didn't tell me any of the equilibrium concentrations of any of the chemical species, I had to use the Kc expression and the given value of 5.10, plug in the equilibrium values for each one of my chemical species in terms of X. I got a perfect square here, and then I solved for X, and then I subbed X back in to my ICE chart and finished up the calculations, and I have my equilibrium concentrations for every single chemical species in this reaction.